Hello, everyone. My name is Tobias Andermann. I am a postdoc currently at Gothenburg University in Sweden and at the University of Fribourg in Switzerland. And here I added a little photo of myself for you to have a photo to go with the voice you're hearing. And as a little disclaimer, I have to say that this presentation has nothing to do with Madagascar per se, but instead I want to present you a computational model that can be very well applied to Madagascar and to modeling the evolution of grassy biomes in Madagascar. So this is a bit of a methods talk with a method that may have potential for Madagascar's grassy biomes. As a brief introduction to this model, it basically consists of training the model and then using the trained model to predict vegetation. And to train the model, we'll need some sort of data. And here I just presented the data we used in this proof of concept study in that we chose to focus on North America. But the same could be done for any other region or for any other spatial scale. So here we have data from climatic models. You see on the top left, those are models of temperature and precipitation, and they are available like through time and can basically be extracted for any point in space and time. And then we have some sort of vegetation information that we'll need to train the model. And this can consist of paleovegetation reconstructions, but also can be supplemented with current information. So you see here in this table, there are some like 3 different vegetation points displayed here, 2 open vegetation points and 1 closed vegetation point. And you see, for example, in the bottom row, the open vegetation point has the age of 0, so that's a present vegetation information point. But this model can basically use data from the past and the present equally to learn associations of climatic factors with vegetation, but also, and that's the real novelty, what's displayed on the bottom, it can also learn the associations of biotic features with vegetation. So for example, we can just use taxon occurrences of any number of selected taxa, and here we used mammal taxa, but really one can use any types of taxa that have a good occurrence record in the present, but also that have preferably some fossil record throughout the time period that we want to predict vegetation for. So yeah, these data we can all throw together into the model and train this machine learning algorithm, and then it will become a trained model that is optimized toward predicting vegetation based on these data. And this trained model can now be applied to predict the vegetation for a set of points that we don't have any vegetation information for. But every point has basically all it needs is a longitude, a latitude, and an age. So as long as it has these 3 coordinates, we can predict the vegetation for these points with our trained model and our data, the fossil data, and whatever other data one chooses to add. So, and I also want to mention the fossil data would be the same for training and for prediction. So it's always the same fossil data set that is being used for predicting. And then when we predict vegetation inferences with our trained model, we do not only get a vegetation prediction, but we get a posterior probability estimate for each vegetation type. So for the first point, we here get something like 93% posterior probability of open habitat and 7% of closed habitat, and so on. And these posterior probabilities can be either plotted as they are. So here on the bottom you see a map with a kind of a gradient between yellow and green, yellow meaning strong indication for open habitat and green meaning strong indication for closed habitat. And so we can create this table of space-time coordinates that you see in the top left in a way that we can basically plot estimate vegetation for a whole continent, for example. If we just put a grid over a continent or over Madagascar or any other spatial scale, we can extract the cell center coordinates, and then for different time slices at the time coordinate and then predict the vegetation label for each cell, grid cell point. So that allows us to make predictions like the one presented here. This is a prediction of open habitats throughout the last 30 million years in North America. And yeah, I'm just looking at the time. I should wrap this up. So I just want to mention briefly that the data that we used in this study, just to give you a bit of a framework or of a perspective and see if maybe you have similar data. We used here 300 paleovegetation points, so it doesn't take more than that to train a model. And it could even potentially work with fewer vegetation points, and they can always be supplemented with additional current vegetation information, which works just as well, but runs the risk of overfitting toward the present pattern and not being so good in detecting past changes. But the fossil occurrences we used here were 7,500 in total, which were belonging to something like 100 selected taxa. But one could select fewer taxa, just focus on those that have a good fossil record for the given time period. And here we also use temperature and precipitation, but also it's not necessary to use these additional features. Just having fossil data and paleovegetation data is enough to run this model. And here we get an 89% and almost 90% prediction accuracy, which is a very or rather decent accuracy for this binary classification problem, especially given that it is like doing this for points in rather deep time throughout the last 30 million years, with a lot of changes that are associated with this vegetation evolution. And I just want to close with this, that the model is very flexible, so it can be used to predict any number of types of vegetation classes. So it doesn't have to be just these two, open and closed habitat, but it could also potentially predict more nuanced vegetation types between, let's say, open habitat grasslands and savannas and deciduous forest and rainforest. So there could be basically a lot of different categories, but the bottleneck here is the number of training data points per class. And it could also be extended or contracted to any given temporal or spatial scale. So in our case study, we predicted the vegetation for North America throughout the last 30 million years. But equally well, this model could be applied for a much smaller spatial scale like Madagascar, and a more focused temporal scale like, let's say, the Holocene. But the bottleneck here is that it would require some sort of fossil occurrence data and paleovegetation data that have a good spread throughout this time frame and have like the necessary resolution, especially the temporal resolution. And really any taxa or abiotic features could be used for this prediction task. So it doesn't have to be mammal taxa, it doesn't have to be climate predictors, it could be a lot of different things like elevation, distance to the sea, anything you could think of that can be measured for a given point in space-time. Alright, that's all from me, and sorry that I went a little over time, but thanks for listening, and I'm excited to be chatting with you guys and hear if anybody is interested in maybe using this model for the data, and maybe I would also be happy to contribute to the review, maybe recapping on some of the existing models that are out there to predict vegetation, and also mentioning this model as a potential outlook for future prediction tasks using a probabilistic framework. So I hope that maybe some people have data that they could imagine running with this, and that this is of interest for the Madagascar grassy biome community. Thank you very much.